In this video, we're taking a look at non-ideal systems and how energy conservation applies. Specifically, we need to understand what's going on with non-conservative forces and the work that they do so that we can combine that with what we know about conservative forces and their energy so that we can talk about the general strategy of conservation of energy, even when we don't have perfectly ideal situations. So when we talk about a conservative force, we haven't really defined what we meant so far. A conservative force is a force that does the same amount of work no matter how you move through it. If you imagine taking a box from the bottom to the top of a hill, the amount of work done by gravity is the same whether you take the blue, the red, or the green path. It really doesn't matter. The force of gravity is conservative, and conservative forces get potential energy terms named after them. Another conservative force would be to stretch a spring. Now, this may not be as obvious, but if you take a spring and you start at some point and you stretch it out to a new point, or you take that same spring and you stretch it out further than B and then bring it back to B, right? It still does the same amount of total work, and the same amount of potential energy is still stored regardless of how you got there. And that's what we mean by a conservative force. And so by that definition, not that many forces follow this rule, right? Spring force, gravitational force, both conservative. But if you think of something else, right, it wouldn't necessarily be true that the amount of work done is independent of how you get there, right? The good thing about conservative forces is they do not change the mechanical energy of the system. And if it's only conservative forces, then we have potential plus kinetic equals potential plus kinetic. And that's what we've done so far. However, right, if this isn't true, then we don't have as simple a situation, right? In the case of a projectile, the force of gravity does work. We get kinetic energy to start, turned into gravitational potential energy, and so on. Right? And on the way down, the opposite happens. The gravitational potential energy turns into kinetic. The work done by non-conservative forces but depends on path. And friction is an easy one to think about. The amount of work done by friction, if moving from A to B along that straight line path, is some value. Whereas if you move it along a much larger path by wiggling it back and forth, friction is going to be always opposing motion, doing work for every little straight segment of that, doing a lot more work than it would otherwise. Right? So friction does work, and it does more work when you follow the A prime to B prime path. When a non-conservative force does work, the mechanical energy is no longer conserved, because that's what we meant by conservation of mechanical energy. And so it either turns into thermal energy, things heat up, or it's transferred between objects in some other way. We'll get to one of the interesting things where it's transferred in collisions when we talk about momentum and impulse. But the force of drag, the force of friction are non-conservative, dissipative forces. They turn mechanical energy into heat, whereas tension and normal force are non-conservative, but they transfer force energy from one object to another in interactions. And so this is a... Cut this piece out. So far, when we've talked about ideal isolated systems, the initial mechanical and final mechanical energies have been equal. This is only with conservative forces like force of gravity and the spring force. But now with a non-ideal system, we need to add something else. We need to say, well, they don't equal, which means there is some change in mechanical energy to make the equation work out. So the initial mechanical energy plus whatever change there was from non-conservative work equals the final. And usually we write it this way. Initial kinetic plus potential plus whatever work is done by non-conservative forces equals the final. This non-conservative work is done by friction or tension or normal force or applied force or every other force that changes the mechanical energy of the system. It could be positive or negative, right? You could have an applied force that adds energy to the system and speeds things up or lifts it up a hill. You could have friction and drag force from air resistance that always are going to be taking energy out of the system, unless, of course, that friction is static and propelling it forward, but you get the idea. So here's an example. If you have a car skidding to a stop, Well, the friction does negative work and the car's mechanical energy decreases. This is a problem we've already solved with kinematics, with forces, and now with the work kinetic energy theorem. And you could also solve it now using conservation of energy, using that work non-conservative term. The mechanical energy is turned into heat. The tires heat up, etc. Right? And so if we wanted to solve this problem and think about what's actually happening, this 1,000-kilogram car traveling at 20 meters per second coming to rest. We are given a distance that it skidded, 30 meters long. What is the force of friction? Well, that's going to come out of understanding the work done by non-conservative forces. We don't have any gravitational potential energy because it's at the same height, which we can call zero. And it ends with the kinetic energy being zero. So we have an initial kinetic energy plus work done by friction equals zero. And in our case, the frictional force times delta R is the work done by friction. And if we solve for the force of friction, we end up with negative 6,700 newtons, or 6,700 newtons in the negative direction. How much of that energy was converted to heat? Well, the work done by friction converts kinetic energy into heat, which is the transfer of energy into, something where you can measure the temperature change. And so the amount of heat is the work done by friction, Fk delta R, which is about 200,000 joules. We could also think about this in terms of what would change if we were traveling twice as fast. How far would it skid? Well, we know that 1/2 mv squared, the initial kinetic energy, is equal to, in magnitude, the amount of work that the friction did. And if we were to double the speed, that would make the left-hand side of the equation 4 times as big, which means the delta R would be 4 times as far to balance that equation. We can also look at lifting something up using a motor. Right? Now, we'll talk a little bit more about motors when we talk about power and when we talk about electricity and electromagnetism. But the basic idea is that the motor can do work on a system. Right? Obviously, that crate will not go up the ramp on its own. The tension does positive work to pull the crate up the ramp, and this increases the mechanical energy. The gain in mechanical energy comes ultimately from the electrical energy that is converted to motion in the motor. That's not something we need to worry ourselves a ton about right now, but that is where it comes from. All right, so if we do a little bit more in detail here, the 500-kilogram crate is lifted up by a constant 4,000 Newton force on the crate. Now, this is a problem that you could certainly have figured out using Newton's second law, but we can also look at it in terms of an energy problem. How fast is the crate going at the top? Well, we know that initial and mechanical energy plus work done by non-conservative forces equals the final mechanical energy. We start with no gravitational energy, no kinetic energy, and at the end, we're going to say we have kinetic energy and gravitational potential energy. We're going to say it's moving at the top. It's not at rest. We can figure out how much mechanical or gravitational potential it has because we know how high up it goes. And we can solve for that V by plugging in the known quantities, and we end up with about 7.7 meters per second. In summary, what we can do when we consider the non-conservative work alongside the work done by conservative forces is that we can use our conservation of energy equations and add an additional term that basically says however much the mechanical energy changed from the ideal situation, we can keep track of it and we can use that to solve problems.